Okay, so here we go. This is section 1.4, part 3, solving trigonometric equations. We're going to start up here in the upper left with solving the equation 2 sine x plus 1 is equal to 0. Now, we start out solving trigonometric equations using algebraic techniques. That is, we're going to isolate not necessarily the variable per se, but the trigonometric function that contains the variable. So I'm going to kick that 1 over to the other side and divide by that 2, and I'm going to get the statement then that the sine of x is equal to negative 1/2. Now, at this point, I need to remove the sine function. So I'm going to do something that we often do. We use an inverse function, and I'm going to take the arc sine of the sine of x is going to be equal to the arc sine of negative 1/2. Now, this is a very traditional algebraic approach to solving this. The challenge that we get with this is that when we do this approach right here, we actually aren't solving for x. What we're actually going to be solving for here is some sort of a reference angle for x. And then what we're going to have to do is we're going to have to take that reference angle and spin that up and turn that into solutions for x. Okay? All right, so let's just walk this through and see what happens so we can talk about it. The arc sine and the sine are essentially going to cancel each other, and we're just going to get x on that left-hand side. And the arc sine of negative 1/2. Sorry about that. Someone was texting me. I thought I was important for the class. All right, so the arc sine of negative 1/2 is going to give me 11. Negative pi over 6. Right? Here's the challenge, though. That's not really right. While it is accurate to say that the arc sine of negative 1/2 is negative pi over 6, it would be inaccurate to say that this is the solution for this problem. Right? If I were to go and take a look at the original problem graphically, right, so I'm going to flip over here to Desmos because I love Desmos, and I'm going to take a look at the equation y equals 2 sine of x plus 1. And my job is to find out when this function is equal to 0. Now, if you see, there are many solutions to this. My challenge is, how do I make sure that I tell the world I've found all those solutions? Because right now, the only thing I've done is I've found this one solution right here of negative pi over 6. So while that is a solution, technically, it doesn't represent all of the solutions. So what I want to do is first I want to take that reference angle that I just found, turn that into any solutions in a standard period for the sine function. Remember, a standard period for the sine function is going to be from 0 to 2 pi, and then go from there. So what are the standard solutions? Well, the standard solutions, or the solutions in a standard period, are going to be the third and fourth quadrant angles that have reference angles of pi over 6. So this negative pi over 6 that I found right here as a fourth quadrant angle is really 11 pi over 6. And then what is the third quadrant angle that has a reference angle that is the same as the one we found with that arc sine, pi over 6? So that's what, like pi plus pi over 6. So what is that, 7 pi over 6 over there? So we've got 7 pi over 6. Now those would be those two solutions. If I go back to the graph, those would be these two solutions here, right? The 7 pi and the 11 pi. So how do I tell the world that there are more solutions? In fact, infinitely many solutions. So if you remember from trig, what we're doing is we're looking for patterns. And what's the pattern there between 7 pi over 6 and 19 pi over 6? And what's the pattern that would give us that next one out here, which is then what? 31 pi over 6. Or if I start with the 11 pi, what's the pattern that takes 11 pi over 6 and then gives me 23 pi over 6 and then gives me 35 pi over 6? Well, depending on how good you are with patterns, you might see that each of those are plus multiples of pi so the standard notation that we use is this 2n pi. Now, depending on who your instructor was, if you had an older instructor, they might write it like this: plus 2k pi. Because it used to be, for whatever reason, they switched from k's to n's. It used to be you'd see k every single time, and now you see a lot more n's. Either way, whether it's k's or n's, doesn't really matter. What we're saying here is that that stands for an integer value, where n or k, whichever one you're using, are elements of the integers. Integers being -1, -2, -3, 0, 1, 2, 3, those guys. And that would represent different multiples of that 2 pi. Okay. All right, so that was a long way to solve that thing. Okay. Now, if you don't like inverse functions and you don't want to use an inverse function approach, you can, and let me get rid of a bunch of this. Delete all that. You could use a different approach to solve this. A different approach right here would be one that you could use if you had a good working knowledge of the unit circle. You could stop right here and say, on a standard period, what are the values for an angle that would yield a sine value of -1/2? And then you would say, well, there's a third quadrant angle and there's a fourth quadrant angle to give me negatives. The third quadrant angle is 7 pi over 6. The fourth quadrant angle is 11 pi over 6. And then, of course, we'd wrap on those 2n pi's to make those work. Now, that requires that you have a good working knowledge of your unit circle. Not everybody has a good working knowledge of their unit circle. So that's why we have multiple approaches. Okay. All right. Let's take a look at this guy. What is being asked here? Uh-oh. I got a problem. This is a more complicated equation. It doesn't just have one trigonometric term. It has two trigonometric terms. It has cosine squared here and cosine there. Now, luckily, they're the same trig function. They're both cosines, but one squared and one isn't. So what this makes it, in my mind, is I'm seeing this as kind of like a quadratic equation. So I'm going to solve this kind of like we solve quadratics. I'm looking at this and I'm seeing x squared plus 2x equals 3, and I'm asking myself, how would I solve that? Because ideally, sooner or later, I want to get to a point where I have the trigonometric function isolated. And so first thing I would do is I would move the 3 over to the other side, and that's going to give me cosine squared theta plus 2 cosine theta minus 3 is equal to 0. And I believe that's factorable. So that's going to give me cosine theta. What is that going to be? Plus 3 times cosine theta minus 1 is equal to 0. Let's see, first gives me cosine squared, outer gives me negative cosine, inner gives me positive 3, which gives me my positive 2 when I add them together, and last times last gives me my negative 3. Yeah, that factors nicely. Now I'm going to make use of that zero product principle because I have two things being multiplied together and the answer is 0. So that means either the cosine of theta plus 3 is equal to 0, or that the cosine of theta minus 1 is equal to 0. I'll start on the left. If the cosine of theta plus 3 is equal to 0, that means the cosine is equal to negative 3. And that tells me this. Right. Because the cosine can't be negative 3. The value of the cosine, the range for the cosine function is -1 to +1. So that means that the outputs of a cosine function are between -1 and +1. Now, I know that there's at least one person out there who's watching this going, but wait a second. If I type cosine, arc cosine, into my calculator and I put in -3, it gives me an answer. Well, if you happen to be in complex numbers on your calculator, that mode, then yes, that does give you a solution. Oh wait, no it doesn't. That was even too big for complex numbers. Oh, that's good then. All right, because there are some trigonometric functions where you can get weird answers in the complex number system. This one just happens to be one that doesn't. Well, that's even better. So we don't have to worry about that piece. That piece has no solutions. So let's look at the other one. This tells me that cosine must be equal to 1. Well, on the unit circle, where is cosine equal to 1? Cosine is equal to 1 when the angle is 0 plus 2 n-pies. Now, you might have noticed something. Nothing in the directions up here told me to work in radians, yet I instinctively started solving everything in radians. And why is that? Because I am in calculus, and calculus is done in radians. If you solve these things in degrees without the problem specifically telling you to work in degrees, you're wrong. That's just it. You are just wrong. Make sure that your default position is always, I work in radians, unless someone tells me otherwise. Right? All right, our third problem to solve here, and then we have some other stuff to take a look at. Let's see, what am I supposed to do here? I'm supposed to solve this. I'm looking at my equation and I've got issues. The biggest issue that I'm seeing, and I hope you're seeing it too, is that there's a cosine over here on the left and there's a sine over here on the right. And if I remember nothing else from trig, it's that if I'm solving trigonometric equations, I need to have the same thing over here that I've got over there. That means that my trig functions need to match. Another issue that I just noticed when looking at it is this isn't the cosine of theta, this is the cosine of 2 theta, and this is the sine of theta. So this is going to give me even more issues because I've got, not only do I have trigonometric functions that don't match, the arguments of the trigonometric functions don't match. So I'm going to have to figure something out to make this thing work. Okay, so to make this thing work, I'm going to have to somehow change cosines into sines or sines into cosines. Now, the only way that I know to change trig into trig, that is just one trigonometric function into a different trigonometric function, is to use some sort of a trigonometric identity. So I know that you have a bunch of them memorized, but in case you don't have all of them memorized, there's this, the trigonometric cheat sheet. Let's see, I'm looking for something that can turn sines into cosines or cosines into sines. Specifically, I'm looking for something that's going to deal with that 2 thing. And I think I found it. I think I found it right here. I think this is it. I think it's the double angle cosine. Now you'll notice that the double angle cosine has 3 things that it's equal to. That does not mean that there are 3 different things. It just means that there's 3 different ways to represent it. The reason being, for these 3 different ways of cosine squared minus sine squared, or 2 cosine squared minus 1, or 1 minus 2 sine squared, the reason that there's many different ways to do this is because Pythagorean identities. Sine squared plus cosine squared is equal to 1. So that means that in any one of these, you could replace either a cosine squared or a sine squared with 1 minus the other squared and arrive at these 3 formulas. Which one do you think we should use? Okay. My bet is this one. And why am I thinking that? Well, what's the other function in the equation? Plain old sine. And this will change cosine 2 theta into 1 minus 2 sine squared. Then I'll have a sine squared. It'll kind of be like the last problem. Then it'll be quadratic. So I'm going to try this one and see if it works. So help me remember this. Cosine 2 theta is 1 minus 2 sine squared. Cosine 2 theta is 1 minus 2 sine squared theta. And that's still equal to 2 minus 3 sine theta. And now I have something that kind of looks like the last problem we did. I've got a trigonometric function here, a trigonometric function here. They're the same function, just one of them squared and one of them isn't. So I'm going to gather up everything and try to do it the same way I did the last one. I'm going to try to factor everything. All right, so what's that going to give me? Let's see. If I move all of this junk to the left, but then that's going to keep that negative. So why don't I move all of this junk? Oops. To the right, and then that will keep, or that will make my squared term positive. Okay, so that's going to give me 0, then is equal to 2 sine squared theta minus 3 sine theta plus 1. Now I'm going to hope this thing factors, because if it doesn't factor, I'm in trouble. And so if it factors, it's going to factor into 2 sine theta and sine theta. Since this is prime, the only way for it to factor is 2 times 1. And now I need to get that negative 3 and that positive 1. So how about a negative 1 and a negative 1? Will that work? First times first gives me 2 sine squared. Outer terms give me negative 2 sine. Inner terms gives me negative sine for negative 3 sine. Last times last is a positive 1. Okay. So I've reduced it down to that zero product principle again. 2 things multiplied together, the answer is 0. One of the other must be 0. So then where are we at? We are at 2 sine theta minus 1 is 0, or sine theta minus 1 is 0. Okay. Now, given that I'm lazy, I'm going to attack this one first. If the sine of theta minus 1 is 0, that means that the sine of theta is 1, and that means that theta is pi. Come on, there we go. That means that theta will be pi over 2 plus 2n pi. Sine is y. Y is 1 when we are exactly a right angle, which is pi over 2 in radians. Now I'll deal with that other one. Okay. When is the sine of theta equal to positive 1/2? Move the 1 to the right, it becomes positive, divided by 2, 1/2. Sine of theta 1/2, positive. That means there's an answer in the first quadrant as well as an answer in the second quadrant. They will both have the same reference angle. That reference angle is pi over 6. So that tells me then that theta is pi over 6, or theta is 5 pi over 6. Of course, we tack on that 2n pi to make it work. So then last thing to do is to wrap it up and make it look pretty and represent all the answers. And so what's my solution? My solution is theta could be pi over 2 plus 2n pi, or theta could be pi over 6 plus 2n pi, or theta could be 5 pi over 6 plus 2n pi. Many solutions. Now, of course, if you don't trust your work, you could always take any of these values, put them back into that original equation, and check to make sure it worked. I believe in myself, so I'm going to go with this. All right, we're at like 18 minutes for this video, so I'm going to call this one here, and we'll come back. The next video will be the rest of the section. It'll be just a basic overview of graphing.